Hi there, this is exercise 1A. It's meant to be a revision lesson on mathematical induction that we saw is part of from the year 12 textbook, and this is from the year 13 textbook, and is meant to go over the types of proof by induction that you're meant to know already. But everyone knows this is quite a tough topic, so that's why effectively do it again. And then in exercise 1B we see a new type of mathematical induction that we've not seen so far, and then hopefully we can do those as well. So anyway, let's get on with this mathematical induction. Remember there's 4 steps. Step 1 is we have a belief that some rule is true, sometimes called a conjecture, and we check to see that the rule works, usually for n equals 1. Sometimes it can be n equals 2 or n equals 3 or something, but the lowest possible number. We then assume that it is true for n equals k, and you have to write that statement. You then have to do the difficult bit, which is the inductive step, and it's a proof for n equals k plus 1. And the last one, nice easy step of writing out the completion statement. You might remember this completion statement. This is the given result with k plus 1 replacing k. Therefore, if it is true for n equals k, it is also true for n equals k plus 1. Since it is true for n equals 1, it is true for all positive integers. Now, what a mouthful that is, but you are meant to learn that and know that, or at least a version of it. I don't mind if it's slightly different. So, here's a question for us then. It says let y equals x e to the x. Now we're looking at differentiation here, and sure enough it asks us to find these 3 things. Now not as easy as it even looks, because dy by dx, this is a product rule, and u equals the x and v equals e to the x. Therefore u dash equals 1 and v dash equals e to the x still. So this equals, when I do it first time, it equals uv, which is x e to the x, plus e to the x times 1, which is just e to the x. Alright, fair enough. So I can actually use that. I just realised I thought this was going to be a bit of hard work, but it's actually not as bad as I thought, because d2y by the x squared basically now differentiate what I just differentiated, and x e to the x is actually what we started off with. So I know that when I differentiate this bit, I'll get all of this bit again. So I know I will get x e to the x plus e to the x when I differentiate this. But don't forget that I then have to differentiate this next part as well, because so far I've only differentiated this. So when I differentiate e to the x, I get another e to the x. I'll come back to that in a bit, but when I then have to do it a third time, d3y by dx cubed, well, I've got to do this x e to the x, which is, I know, is going to give me this lot again. That's x e to the x plus c to the x. But then, obviously, this bit was x e to the x plus 2e to the x. So when I now differentiate this bit, I get another 2e to the x, which is x e to the x plus 3e to the x. And I've now got 3 answers. 1, 2, 3. And it says find a conjecture. Actually, write it as conjecture and an expression. Find a conjecture for the nth differential and prove it by induction. Well, now let's just think for a moment. The nth differential. Well, I suppose I could just tidy this up a bit. If I just take out e to the x as a common factor, I'll get x plus 1. I'm not sure if this will help, but on this one I'll get e to the x, x plus 2. This does help, I think. And this one is obviously e to the x, x plus 3 in brackets. Now that effectively means that I think that dny by dx to the n is going to be e to the x plus n. That's what I think it is. I mean, that must be what it is. But then I've got to prove this by induction. So I'm going to go step 1. I don't think I'm going to get through all these examples I've got for you. I think I've got 3 or 4 examples. I'm not going to get through them all within 15 minutes. I think this will be 2 videos just for this. But anyway, step 1. I think therefore that if this is true, the left hand side of this says d1y by dx to the 1, if you like, and we know dy by dx is e to the x plus 1. This is the right. I don't know why I've done this really. I don't think I needed this really. X plus 1, which is of course what we got. This is true. So chucking 1 into our formula agrees with what we had right at the start. So I'm happy with step 1. Step 2, we have to assume that dk to the y, dx to the k is equal to e to the x plus k. So that's our assumption. I have to clear away some space here, so I'll erase everything. So now I've got that, I'm going to have to try to do step 3. This is the inductive step. Now it's actually not so bad with differentiation. It's not the easiest one, but to get dk plus 1 y by dx to the k plus 1, you've got to realise really all you're doing is you're differentiating what you already had. And what we had was the assumption, actually I'll write this down first. What we had then was the assumption that we know, oh that's okay, we know now that dk by dy dx to the k, well I've assumed it's something, and I have assumed it is equal to e to the x x plus k. And effectively I have to differentiate this thing again, and if I get what I've said it is, then it works, and I don't think that's the worst. So if I just, it's a product again, u equals e to the x, u dash equals e to the x, v equals x plus k, that's a v, v dash equals 1, so therefore when I differentiate this thing, I get e to the x times 1 plus e to the x times x plus k, which equals e to the x plus e to the x plus k. And essentially I can take e to the x out as a common factor of these two expressions. I get x plus k from here plus the x1 from here, and it's done. And this is why you need the completion statement where you would write this is the given result, and I'm not going to write it out, I'm going to let you know that you're meant to write it out, but this is the given result, blah 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 blah, and that is then proven. But it's taken 9 minutes to do that, so I'm definitely going to need more time than I allow myself. Second question, so a sequence is given by u1 equals 2 and un plus 1 equals 3n plus 2. Prove that the nth term for the sequence is u equals 3n minus 1. Okay, so well, first of all I need to, step 1, I need to check. So I'm going to write check for n equals 1. And if I go to my rule, it says that u2 will be 3 lots of u1 plus 2, and I know that u1 is 2, So that's 3 lots of 2 at 2, which is 8. Now, if I go over here, I've got this alternative way of looking at it. So it says U2 will be 3 to the 2 minus 1, which is 9 minus 1, which is 8. So step 1 is true. Step 2 is I've got to write out that assumption statement. That says step 2. We assume that U to the K, and it's a bit annoying, you have to change the letter, but that's the way it goes, I suppose. Okay, so now clear my screen. And now I've got to do my step 3. Now this is the inductive step. And here I'm going to have to use my formula. This is quite nice, to be honest. My formula says UK plus 1 equals 3 lots of UK plus 2. That's what my formula told me. So I can therefore chuck, since I know what UK is, I've assumed it in step 2. It's 3 lots of 3 to the K minus 1. Now, this is 3 times by 3 to the K minus 3. Which is, of course, 3 to the K plus, oh, I made a mistake there. It's 3 lots of that plus a 2. Plus a 2. So anyway, it's 3 times 3 to the K, well, that's like 3 to the 1. So that's 3 to the K plus 1 when I add the powers. And minus 3 plus 2 is minus 1. Ah! Which is what my rule said. So this is where we write step 4. This is the given result, and you again would write it all out. Given result, blah 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 blah. The third one, I'm not sure how many there are. There's 2 more, so I definitely won't finish in the next 3 minutes, which is all I've got. So I'll get partly way through this. In fact, I'll stop there, and then we'll do the next 2, and then we'll put you on to the exercise. So we'll stop that there.